In this video, we will be using matrices to solve systems of equations with the goal of translating an augmented matrix into its reduced row echelon form. But in this very first video, what I wanted to do first is solve it in the more traditional algebraic method, and then we'll compare what we're doing in the matrices to the more traditional approach as we go. So let's go ahead and solve this system of equations the normal way, or whatever you want to call it, which is often referred to as Gaussian elimination, basically using elimination to solve the system. So let's go ahead and call these equations 1, 2, and 3 in the example from the packet. And we'll add them together in some combination in order to eliminate the variables. And in this case, what I'm going to do is I'm going to start by eliminating x, just because that's how we always do it with the matrix method. But as I taught you guys in the previous videos, you could eliminate y or z, which might make more sense because their coefficients are simpler. But I'm just going to do x to try to be programmatic with how it works with the matrices. But basically, let's say I wanted to take equations 1 and 2 and eliminate x in those. I would want to take equation 1 and multiply by -3. That way, these equations would be ready for elimination, because x, when I add them together, they're not going to work. So what I'm going to start with is take equation 1 times -3, which would be -3x minus 6y minus 3z equal to -3. And I'm going to go ahead and leave equation 2 alone. Whoops. Equal to -4. And this would leave me with a system where the equations are ready for elimination. I could then add them together. That would eliminate. Or again, I could think of that as 0x. And then this would be -7y, -5z, and -7. And this would give me, as I said before, a new equation, equation 4, which has an x, in which x has been eliminated. And essentially, this equation is going to be a new row within the matrix as I'm using the elementary row operations to help solve that system. And then what we would do is we'd take another pair of equations, say for example equation 1 and 3, and add those together in such a way that those will eliminate. And here, if I took equation 1 times 2 first, that would give me 2x plus 4y plus 2z is equal to 2. Remember that you want to make sure to multiply every single term in the equation by 2 when you are multiplying, because that's how multiplying an equation works, by distributed property. And then equation 3, I'm going to leave exactly the same. And this would give me, again, I want to eliminate the same variable twice so that I get a new system, which is, again, the strategy we talked about before, but that would leave me with 2y plus 3z is equal to 13. And this would be like my new equation, equation 5. And essentially, I have now eliminated x and y. But now I could take equation 4 and 5, and I could try to eliminate y from them. So since equation 4 has a coefficient of 7, and 5 is a coefficient of 2, I want to multiply them by their respective coefficients, or by the opposing coefficients. So if I do 2 times 4 and 7 times equation 5, that would leave me with -14y minus 10z is equal to -14. And on the second equation, it was 7 times 5 would be 14y plus 7 times 3 is 21z is equal to 7 times 13, which is 130 cut in half is 65, plus 26, 88. No. 91. I'm going to do that in the calculator just because I don't want to mess up any individual steps. 13 times 7 is not something I have memorized apparently. Yeah, 91. Okay, just making sure. But anyways, now with equations 4 and 5, those are ready for elimination. I add those together. That would leave me with 11z is equal to 77. I could then divide through by 11, which would give me 7. And from there, now our system is in triangular form because we have z equals, and I could kind of go back to realize that if I use equations 1, 4, and if we called that 6, what I now have is a system in this form, which is basically ready to solve. Once I have one, all I need to do is back substitute to find the rest. And this is basically what we call the row echelon form. To get into reduced row echelon form, then we're going to back substitute and solve from there. So basically, now how would we do it using a matrix, using an augmented matrix and using the elementary row operations? But the reason I went through all that is it's pretty much the same method. We're just using a different set of rules called those elementary row operations. Excuse me. And we're starting with the augmented matrix. So where I want to begin is taking this matrix into its augmented form. So we'd have 1, 2, 1, 1, 3, minus 1, negative 2, negative 4, negative 2, negative 2, 1, 11. And this is how I'm going to begin. So instead of doing a bunch of algebra, what I'm going to be doing is working on this matrix, applying those steps in the elementary row operations, which are these 3 rules. You can do them in any order you want, but we're going to be applying them strategically in order to make our matrix in triangular form. Basically, the same thing we want to do here. So as I imagine it, my goal is to transform the matrix into this. Basically, I want to get it in the form of 1, 0, 0, 1, 0, 1, triangular form, where my diagonal is a series of 1s, and then work my way up to get it into reduced row echelon form by doing this. And essentially, the way I do that is by adding the rows together in the same way we did with elimination. So basically, I'm just going to walk through an example. I'll do one more example in the next video. And this is going to be hard. This is probably going to be hard to follow because there are lots of steps involved, and it is not an easy process. But basically, I want you guys to kind of get the idea of how this works, and I'll then teach you how to do it in your calculator. And on the final, I'm going to want you to understand the basic concept of matrices, but I'm not going to actually make you do every one of these steps by hand. Since a calculator can do it, that's the ultimate goal of why I'm getting into this, but I don't like to teach you guys how to do it in a calculator without first understanding what it is we're really doing and the idea of simplifying a system into a matrix and kind of how that all works. So I'm not saying don't pay attention, but I'm saying that this is something that's harder to learn than 1 week of class time is granted. So I'm not going to be expecting you to do all the elementary row operations to completely solve a system, but I think a lot of you will be able to figure it out just fine. But it's something that definitely takes a lot of practice to be able to do by hand. So anyways, let's get to it. But basically, if I'm looking at a system of equations, and it is in augmented form, my goal is to translate these into zero. So what I'm initially thinking about what to do strategically, because technically there's not a correct order, is to first turn these guys into 0, which will mean I'm eliminating the variables of x, kind of like I did in these 2 steps, right? I canceled out x, I canceled out x again. That's a necessary series of steps when solving a system traditionally. So basically, and I'm allowed to add multiples of rows together. So the first thing I would do is if I want to turn this first one into a 0, what I could do is I could start with row 1 and add that to row 2. If I first take row 1, and the way I could actually keep track of what I'm doing is by enumerating what's happening in each step, is I'm going to take negative 3 times row 1 and add that to row 2. And like the way that I'm writing this is just the way that I could kind of keep track of what's happening as I'm working through my matrix. But this is something that as you practice it, You can do this faster in your head without necessarily having to show each of the steps. But if you look at the book in chapter 6.4, they're going to be showing their steps in a very similar way, where they enumerate exactly what row is being added to what other row. And what I remind you to focus on is, why am I doing this? It's to cause an elimination, basically, to cancel out this 3 and make 0. But basically, if I do that, I'm going to keep the first row the same because my goal is to put 0 in specifically those spots in red, and I'm allowed to change the rows as I add them together. That's kind of the idea. But what I would get is, well, negative 3 times 1 plus 3, that's going to make 0. And the whole reason is that's the goal. I'm trying to turn those red elements into zeros. Then I'm going to do, well, I have to make sure to do this whole thing all 4 times to each of the 4 columns within each of those rows. So I take negative 3 times row 1 and add that to row 2. So that's going to be negative 3 times 2 is negative 6, plus negative 1 is negative 7. And that would give me the new element here. I'm going to take negative 3 times 1 and add that to row 2, which is negative 5. And then I'm going to add negative 3 times this, which is negative 3, plus negative 4 is negative 7. And what that will leave me with is that new element right there. And in the same way, my goal is to make this element a 0 as well. So in order to do that, I need to take 2 times row 1 and add that to row 3, because that's the only way to take this row and add them together in a way to make 0, right? Because I want to always multiply this number by, it's like I'm always multiplying by them by the reverse coefficient so that they will properly cancel. And so again, I need to do that to all the other elements. So again, that would be 2 times row 1 plus row 3. It's 2 minus 2 is 0. So that will make 0. That's good. Then I'm going to do it to the next column. 2 times row 1 is 4 plus row 3 is minus 2 is 2. Then I'm going to take 2 times row 1, add that to row 3. 2 plus 1 is 3. And then 2 plus row 3 is 2 plus 11 is 13. And basically, I've started off with my primary goal, which is to get zeros beneath the first one, as was initially my primary goal. And then again, my goal is to work my way through the zeros in a very specific way. But also, if we return back to the math we did a minute ago, the elimination way, notice that what I'm getting is exactly the same equations I did before, because I was following the same strategy, right? I'm eliminating the variables x, which generates a new equation, negative 7y minus 5z minus 7. 2y 3z equal 13. It should be the exact same way as if I was to do it using the algebraic process, which is called Gaussian elimination. Now, when we do it in matrix form, it's often referred to as Gaussian Jordan elimination, which is just the name for this process. But it's really the same thing. It's just when we're doing it in matrix form using those elementary row ops, it takes on a different word. And then basically we can keep operating on this matrix in order to make it simpler. So the next goal is to get a full triangle of zeros and get it into upper triangular form. Basically, to turn those into all of them into zeros in order to help progress and get those zeros in the desired way. Because again, the kind of the idea here is I want to first get into triangular form, which was this form like here, where I have 1, 1, 1, 0, 0, 0. And then once you do that, it will become much easier to finish it. And I'll just finish this example because I didn't really explain that very well before. But basically, next I'm going to use row 2 and row 3. I can then add these together to formulate 0 in this spot, which is what I want to do next. And so basically, I'm going to leave row 1 alone. I'm going to leave row 2 alone for now. And what I want to do is I want to take the previous row 2, so I could take 2 times row 2 and add that to 7 times row 3, and that should make the desired 0. Again, the goal here is to add these two together to get 0. So if I take 2 times this and 7 times this, it will make negative 14 plus 14, and then those will eliminate. And I do this all the way across. So notice that since these are zeros, if I do all of this math and I take, 2 times row 2 and 7 times row 3, that's just going to be 2 times 0 plus 7 times 0. So this 0 will actually stay the same. And the goal is once you make a 0 in your matrix, in the matrix procedure, that will stay 0. Then in the next row, I'm going to take 2 times row 2 plus 7 times row 3, which is negative 14 plus 14, which is going to be 0. Then I'm going to take 2 times row 2, negative 10, plus 7 times row 3, negative 10, plus 21 is 11. And then I'm going to take negative 7 times 2, which is negative 14, and add that to 7 times 13, which is 85. Sorry, 7 times 13 was 91. We did that math a second ago. 91 minus 14 is 77. And notice that what I end up with in this last equation, notice that this math is fairly challenging to do in your head. And the only reason that, I wouldn't say it's easy for me, but it's a little bit simpler for me is because I've done it a lot of times and I've taught this subject quite a few times in my life. But there's a lot of numbers to keep track of, and ultimately your calculator can do all this math for you. That's kind of what I'm driving at here, but I wanted to sort of show you how the calculator does this and the kind of how the procedure works in a way that we can program a calculator to actually do. But then additionally, what we're allowed to do is multiply a row through by a non-zero constant. So what I could next do is take row 3 and divide it by 11, which is the same as multiplying by 1/11th. And that would simplify my row 3 down to 0, 0, 1, 7. And then notice that row is now quote unquote solved. Or as I was doing it when I was working on the system of equations before, I don't know why the 1 and the 2 did not copy there. There they go. But what I end up with is the equation z is equal to 7, much as I did before. I'm just doing all the same math in the matrix format instead. And then once I have it in triangular form, technically this we often want to get as ones as well, because this equation looks kind of ugly. And if I want to get this into a 1, I could have taken that equation and taken row 2 and divided by negative 7. Basically, you just divide by the coefficient. And that would leave me with 0, 1, 5/7, 1. And you technically don't have to do that step because now I have fractions, but now it is in row echelon form because it's in upper triangular form, and the diagonal is a series of 1s. And again, this is basically the equation is now going to be very easy to solve because now that I know z, I could reverse the substitution to find y and x, so forth. But the way we get it into reduced row echelon form is by finishing the remaining triangle of zeros, and basically, which is the final goal, to get the upper triangle, or this triangle of zeros, as well. Because if I do that, and if I leave all those others as 1s, it will basically, I have z, it'll be x, y, and z all solved completely correctly. And what's nice is once I've solved for z, this is the same process of back subbing. I could actually add my way back up to finish solving for x and y. And so let's go ahead and do that. I'm running into the math I did a minute ago. And sorry, this video is getting way too long, so I'm trying to finish this up as literally as fast as I possibly can. But basically, I'm going to take row 3, and my goal is to make this into a 0. So if I wanted to make this into a 0, notice that these numbers aren't very good. And the exact steps which I just did to get the previous coefficient to 1 now has introduced the possibility of fractions. But if I just took negative 5/7 times row 3 and then add that to row 2, that should cancel out the 5/7 and make that a 0. And if I just took -1 times row 3 and added that to row 1, that would cancel the 1 there. So it's kind of like my real goal here is to make these into zeros next. And then once I get those into zeros, there's kind of a process of eliminating variables in a particular order that if you do it in the same order every time, it makes this process a lot easier to follow. But basically, let's go ahead and do those 2 steps which I've just enumerated. So I'm going to leave row 3 alone now because row 3 is now solved because it's now just says z equals 7 and I don't want to mess with that. So now my goal is to mess with the previous 2 rows to make zeros in those other desirable locations. So if I do -5/7 times row 3, well, 0 times -5/7 is still 0, plus 0 is still 0. 0 times anything plus 1 is still 1. And then I'm going to do -1. Sorry, 1 times -5/7 is -5/7, plus 5/7 is 0. And then 7 times -5/7 is -5. -5 plus 1 is -4. And that should give me the value of y, which we didn't actually solve before, but we can double check as we're returning to our previous math, right? Because if I was to now take the z, plug it back in to equation 4 or 5 or whatever, let's go ahead and just use equation 4. It said the -14 times y minus 10 times z is equal to -14. But basically, I could have then found y. That's going to be -14y minus 70 equal -14. Add 70 to both sides would give me 56. And dividing by -14, 56 divided by 14 is indeed exactly -4. And I can see, I get the same answer. And the reason that this is working as I'm working on the augmented matrix is I'm literally doing the same steps. I'm just adding the rows together. I'm multiplying them through. And again, the goal is to produce zeros in the correct locations. If you've put zeros in the right places and used the elementary row operations correctly, it's doing the same exact thing. And then also, let's go back and keep working on it. I also want to make put a 0 here, which if I follow what I did here, if I take -1 times row 3 plus row 1, that should put a 0 up here as well. And again, the value of the zeros is once I have 0, it will not change anymore because I'm going to get 0 times -1 is 0 plus row 1 is 1. Then I'm going to get 0 times -1, 0 plus row 1, still not going to change 2. Then -1 times -1 is -1 plus 1 is 0. That's again why I was multiplying here because I'm imagining adding these 2 equations together. And since I want to cancel this one, that's why I'm multiplying this one by -1 because this one times -1 plus this one will produce 0. And then this will change the final coefficient because I'm taking row 3 times -1, which is -7 plus row 1, 1, -6. And now the last thing I need to do is get the final 0 here. And if I can put a 0 there, that will have changed my matrix into reduced row echelon form. For some reason, that's not showing up. I circle it again. I need a 0 there. I don't know why this is not showing up. For some reason, it is not copying my writing anymore. I guess that means it is time to give up on this video. And I guess we'll go ahead and do that in the next one. Oh, nope, here it goes. It's just got slow, probably because of how much writing I'm doing right now. But yeah, I need to get a 0 right there, and then it will be in reduced row echelon form. In other words, it will have been solved. So in order to do that, I'm going to use row 2 and row 1 together to cancel out that 2. And so, because this one is a 1, I need to multiply this by -2 and add it to this to get 0. So I'm taking -2 times row 2 and adding that to row 1. And that should be the final step in getting it into reduced row echelon form. And then So if I'm going to do that, I'm going to take negative 2 times row 2, which is 0, plus the first row is 1. 0 plus 1 is 1. Then 1 times negative 2 is negative 2, plus 2 is 0. Then I'm going to take negative 2 times 0 is 0, plus 0 is 0. And notice that those zeros, if I'm following the strategy in the same order that I'm doing it, it will not ever change the zeros. Because that's the goal, is to produce zeros and keep them 0. And then in the final step, I'm going to take negative 2 times row 2 and add that to row 1. So negative 2 times 4 is 8, minus 6 is 2. And this should give me the solution, the final answer to my system. And from this, I can extract that x is equal to 2, y is equal to negative 4, and z is equal to 7. But basically, I'm going to get my solution to my system of equations without having to do any traditional algebra, just by doing these strategies. And now that I've wrapped this all up, this video is way too long, but in summary, basically there's a series of steps that I can do. If I do them exactly the same way every time, and I'm simply matching the coefficients properly, I will solve the system. And so the synopsis of all this is that we could have a computer or a calculator do exactly this math, perform the elementary row operations in the exact same order to cancel variables, and teach a computer or a calculator how to solve a system without having to do the algebra. And this is not actually the only way of solving systems using matrices, but it's one of the more well-known methods of solving systems. But anyways, in the next video, we will do another example of using the elementary row operations to solve a system, and then I'll teach you how do you solve them with your calculator, because all of this is quite elaborate and it's quite there's quite a lot of steps. Like, if you trace back to all the math I did, I probably had to do about 200 calculations to get here. But the point is that if you really learn this, what we call linear algebra, it actually makes solving systems easier and simpler. And there's actually an argument to be made. Well, is this actually any easier than just doing it this way? Personally, I say no. I think this is probably harder than the traditional method. But what if we move on to harder and harder systems? Let's say we had a system of equations with 4 variables and 4 unknowns, or 5 variables and 5 unknowns, or say 20. Then solving the system by hand becomes so difficult. But it becomes easier to apply the matrix operations to this and solve it using a matrix. It actually becomes easier. And obviously, we could teach a calculator, or not teach, but program a calculator to follow these steps. And basically, the idea behind solving more complex systems is the same procedure, just we have more and more data. We're trying to create a larger and larger system in reduced or echelon form to solve that more complex system. Well, anyways, that's it for this video. Let's do one more in the next.